Come on. Okay. Let's quickly review what you probably did in the previous class. I believe you started the topic called regression analysis, right? And what you did, as far as I understand, was just a simple linear regression, right? You used the data file with prices of used cars, right? Toyota Corolla, correct? 1,000 observations. And the idea basically was that if you have two variables, x and y, so in our case, y is the price of the car, right? And the x, which variable did you select to be the predictor? Mileage, right? Mileage. The idea is that the price of the car, used car, can be predicted knowing something that seems to be related, okay, to the price. And one of the strongest things is the mileage, right? So the idea is if the mileage is low, price tends to be high, right? And as the mileage gets higher and higher and higher, that probably is what happens, right? So if you go to the used car dealer's lot and collect prices of many cars, you will see a cloud of points like that, right? So hopefully you should be able to fit the straight line that doesn't exactly connect all these points, because it's impossible to connect them all, right? But hopefully captures the essence of what is going on, right, in your data set. Let's go ahead and recreate the analysis that we did. So go ahead and start jump. You did that in jump, obviously, right? No. You didn't use jump? All right. JMP, right? That's what I mean. Not jump as in yeah, but JMP. Okay. Download the file Toyota Corolla, right? It's Toyota Corolla 1000, I believe. That's the name of the file. Okay, and go ahead and open it up. So you should see something like that. Okay? So the idea basically is, let me go back to the drawing board, you're going to, we will try and find the best straight line equation that fits the points, right? So in other words, my goal here really is to do something like that. Price, that's my target variable, right, is equal to beta 0, that's the intercept plus beta 1, that is the slope, right, slope, multiplied by the value of the mileage for the car, okay? So I'm looking for these two things, beta 0 and beta 1, that's what I'm primarily concerned about, okay? So let's quickly reproduce what you guys did in the previous class. We need to go to either analyze fit model, right? Or there is a shortcut right here, fit model. Click. Okay. So I select the price as my target variable y, and I select the mileage as my independent variable or predictor or effect. Jump calls that effects. Okay. Mileage is my x. And then I click the run button, and here is my output, right? So a couple of things. Well, more than a couple actually. The very important, the main section, the main result of the jump analysis, everybody is with me? You're able to catch up? No? Not yet? Fit model, price is your y, mileage is your x, and that's it pretty much, right? So the main section of the output is right here at the bottom. It says parameter estimates. That essentially gives me my equation, right? So intercept, estimate of the intercept is 15,816, and intercept of the estimate of the slope is minus 0.063. By the way, minus sign for the slope mileage. Does that sound reasonable? Is that consistent with what I expect? This thing? Yeah, right. Because I'm expecting the negatively sloped line, right? Mileage goes up, price goes down. So therefore, the slope has to be negative, right? So I got my both estimates, right? Right here, 15,816.8. All right, let me write it down. So my equation is like this: price equals to 15,816.8 minus 0.06. Gosh, I don't remember. 0631 times the mileage on the car, right? And after that, I can use this equation, right? I can find a car with 10,000 miles on it and just plug 10,000 instead of mileage, and the result will give me an estimate of the price for this car, right? So let's do a couple of things. Number one is, let's go ahead and interpret the slope with a minus sign, right? And this one right here. What do I mean by that? Let me start over, okay? Suppose, let me write it all over again, okay? Price equals to 15816.8 minus 0.06, whoops, 631 times the mileage, MIL, okay? Suppose I take a car with a certain mileage on it and I drive it extra mile. What's going to happen to the value of this car? Go up or go down? Go down, right? It's getting more used, right? By how much? So this is my old price before I drove the car, okay? So new price after 1 mile, extra mile put on it, is going to be same equation, 15816.8 minus 0.0631 times, now my new mileage is whatever it was before, plus 1, right? That's what Christmas is all about. So 15816.8 minus 0.0631 times my old mileage, right? And that is my old price, right? That it was before I drove extra miles. So this is my old price. Minus this 1 gives me 0.0631, right? So how do I interpret the slope? I put an extra mile on the car, the value went down by that much, okay? So every extra increase, 1 unit increase in my independent variable changes my target variable value by that much. In my case, every extra mile reduces the value of the car by 6.31 cents, right? That's essentially how I interpret that. Does it make sense? Because the prices are in terms of like dollars, right? So 1 extra mile takes off that many dollars from the price. So it's 6.31 cents, right? So that's my interpretation. Okay, now let's go ahead and try to interpret that number, the vertical intercept. Well, here is my temptation, okay? What happens if I put mileage equal to 0? That would mean that whatever is the slope multiplied by 0, that is gone, right? And therefore my price is that much, okay? So therefore price equals to 15816.8 is the value of the car when mileage equals to 0. How do we call a car with mileage equal to 0? Brand new car, right? That's my temptation to interpret, okay? But I have to be careful. Why exactly is that? Here, I don't know if you heard about that, but what happens if you buy a brand new car from dealers and drive it off the lot? What happens to the value of the car?
It loses like $5,000.
Yeah, immediately it plunges, right? Why? Because it's not new anymore, it's used, right? It changed the status. So therefore, it's not completely crazy idea that maybe the price actually behaves like this, okay? Depending on the mileage, the price behaves like this. This was the brand new car value, right? And then first few miles, it drops severely, right? Like this. And then kind of flattens out. Is that possible? Yeah, it is possible, right? So what happens if, for example, I am using to build my regression this range of points right here, okay, starting from, I don't know, 10,000 miles and all the way up to 50,000 miles. Well, if I'm able to set mileage to 0, that means that I'm kind of assuming that the regression continues like that, right? Even for small values of mileage, it's still valid, right? While in actuality, it may behave differently. So therefore, I have to kind of look at my range of the values for the mileage that I used to build this regression, okay? If my range of the values includes values close to 0, that means that my points actually are all over the place, including from here, right? And therefore, it's safe to interpret mileage equal to 0 gives you the value of the brand new car. Otherwise, if I'm using this type of the range, right? Not necessarily true, because, you know, I'm assuming that the equation will continue like that. May not be the case at all, okay? So how do I find out? Well, let's go back. I'm going to put this window down. Let's look at the distribution of mileages, okay? So I'm going to click on the distribution and take the mileage and just look at how mileages are distributed. Now, you probably know that jump by default puts the distribution vertical, right? We're more used for the distribution to be horizontal, so we have to stack it. Well, first of all, is it a symmetric distribution? Let me ask you that question. No, right? It's severely skewed, right? We have many more cars with low mileages than we have cars with high mileages in them, right? But let's take a look at the range. My minimum and maximum. Minimum is 1, right? So part of my data set was actually a car with 0 mileage on them, almost 0 mileage on them, right? So therefore, I actually did build my regression having cars with low mileages. So therefore, let me go back to my interpretation. Therefore, in actuality, my range was more or less starting from 0, right? So is it a valid interpretation that I had before? Hold on. That gives me the price of the brand new car? Yeah, it is, right? Because low mileage cars is the part of my data set. I did use cars with all over the place mileages, right? Including very low mileages, right? So that's a valid interpretation, okay? All right, now how good of the model is that? R squared, right? Let's take a look at R squared. Here is my analysis. The idea here basically is that I'm going to try and build the model that follows my points as closely as possible, right? That would be the best goal for me, right? Obviously, the points are all over the place, right? So they do not fit the straight line, but I want to pick the straight line that fits them the best, okay? And R squared, which is reported right here, summary of fit R squared. Did you discuss the standard interpretation of R squared? How do we interpret that? What does it tell you, R squared? Here is the standard interpretation, okay? Valid for all regressions, all kinds of equations, okay? So R squared gives you the percentage of variability of target variable y, okay, which is explained by and attributed to the variability of independent variables, right? Which is explained by and attributed to variability of your independent variables axis, okay? That's the general interpretation for all regressions, all situations, okay? So it tells you how much of your target variable is explained by the predictors that you picked, simply put, okay? R squared is the value between what and what? Cannot be less than what and not more than what? What's the smallest it can be? 0 to 1, right? So if you have R squared equal to 0, that's the worst model in the world, right? Doesn't explain anything at all, right? If you have R squared 1, that means that you have perfectest model out there, okay? Explains 100%. No doubts about that. But in actuality, it's never 0 and it, gosh golly, never 1, right? So typically it's between 0 and 1, but the closer to 1, the better it is. So let's take a look at our R squared. Our R squared is 0.355. How do I interpret that? Well, again, following the general interpretation, but specific to that problem, I can say that 35.6 or almost 36% of the variability in terms of prices from one car to another car is because different cars have different mileages, right? So changes in mileages from one vehicle to another vehicle are responsible for about 36% of the variability in cars' prices, okay? So, question is, 36% is explained by mileages. Is it good or is it bad or is it okay? Unfortunately, there are no guidelines here. Closer to 1, the better. So 0.99 is great. 0.95 is good, right? 0.8 is actually also cool. We have 36%. Is that great? Well, for one single variable, it's very decent accuracy, okay? The fact that one variable by itself explains 36% of what's going on is awesome, okay? But certainly there is room for improvement, right? Clearly, okay? Make sense? All right. Did you discuss the hypothesis that we test for regression? No? Okay, cool. Let's go ahead and do that. True or false, ladies and gents? here is my regression equation, right? Here's my regression equation, right here, okay? Does it look like to you that my slope has very low value, close to 0? 0.0631, right? So, here's the question. Could that be that I got this equation purely by accident of random selection of cars? In other words, I got these 1,000 cars, and it was such cool sample, or bad sample, I don't know, right? That just happened to show me the slope, right? But in general, there is no correlation, there is no dependency, nothing is going on. That's possible, right? Because that is based on sample. Sample is not everything, right? You get lucky sample, you get results. You get unlucky sample, it will not show anything, right? So here is what I'm going to test, hypothesis testing. So let's discuss that, okay? Null hypothesis, you remember that from statistics, right? From VUSN to 31. Every time when we test hypothesis, there are two of them. There is null and alternative, right? So here's what I'm going to test. Null hypothesis, I'm going to say my slope, beta 1, is equal to 0. What happens, in other words, I can take my slope from in my equation, right, and just replace it with 0, and that will give me just as good of a model as what I have right now, okay? What happens if the slope equals to 0? Let's take a look. So in other words, I'm going to take this value and set it equal to 0. After that, does it matter what kind of mileage the car has? No, not really, right? If the slope is equal to 0, multiplied by the mileage, whatever the mileage is, the answer is 0, so price doesn't change, right? So mileage doesn't really affect anything. Not the price, certainly, okay? So, yeah, here, right? So, if I find in favor of my null hypothesis, it's the same thing as to say that my model is not significant, right? Model is not statistically significant. Statistically significant. Okay? Now, alternative is, you may remember, always what null is not, right? It's opposite. Okay? So my null says that the slope can be set to 0. Can you guess what my alternative should say? If null is 0, an alternative would be non-zero, right? So therefore, slope, no matter how small it seems, cannot be set equal to 0. In other words, slope, whatever it is numerically, has to stay in the model. We can't replace it with 0. It's going to be a different model. It's going to be a worse model, okay? So that's what I'm testing. Now, do you remember how we conduct the hypothesis testing? What do we need to proceed? Choose between null and alternative. What kind of stuff do we need? P-value, right? So we need to find out the p-value, and then what happens after we get the p-value? We have to compare it against a measure, right? Is it a large p-value or is it a small p-value? Okay? So in statistics, the measure of how large or small p-value is called significance level, right? Alpha, significance level. Significance level. Okay? Statisticians use 3 standard values for significance level, okay? So alpha can be 0.1, 10%, or 0.05, 5%, or 0.01. I mean, that's not to say that it can be anything else. Yes, it can, right? But as a matter of practice, typically statisticians are accustomed, are used to using these 3 values, okay? So if my test is conducted using alpha 0.1, that's considered to be a weak evidence, because 0.1 is a relatively large number, okay? It's not very hard to reject the null hypothesis if your p-value, if your alpha is 10%. I can have a relatively large p-value such as 7%, and I would reject, okay? So that's considered to be not a rigorous test. 0.05 or 5% considered to be standard, right? So most statisticians, when they report findings, they use 0.05, okay? And 0.01 considered to be a rigorous test, okay? So in order to reject the null, you have to have really, really small p-value, really convincing evidence to support your alternative, okay? So that test is considered to be more rigorous. Okay, so what happens, how do we test the hypothesis? Let's say I get the p-value. If p-value is less than alpha, what do I do? If p-value is less than alpha, there are 2 options, right? I can either keep the null or reject the null. So if p-value is less than alpha, what do? Reject, right? I reject the null hypothesis, right? Always reject null hypothesis. And if p-value, whoops, it's moving. If p-value is greater than alpha, I fail to reject, right? Fail to reject null hypothesis, okay? So that's kind of a reminder what you should have learned about, 2 years ago when you took statistics, right? That's how hypotheses are being tested. Okay, so here's what I'm testing, right? Is my model significant? Is my alternative true, or is it not significant? Or is it purely coincidental thing what I just found out? Is my null true? So I need a p-value. Where do I find it? Obviously in the output, right? Okay, so right here, where we have analysis of variances, right? So every time when this hypothesis is being tested, software computes the F ratio. I'm not going to go into the details what it is, because it would be opening a separate can of worms. We don't want to go there, right? And probability greater than that F ratio is your p-value. So there it is. Oh, look at that. If you point to the value, it will give you precise number, right? Precise number p-value 2.44 e minus 97. What the heck is e 97? What does that mean? Are you familiar with scientific notations? Yeah, what does that mean? E minus 97.
It's just 96 zeros before that number.
Yeah, 10 to the minus 97th power, right? It's astronomically small number, okay? So here, my p-value is certainly less than, it's practically 0, right? It's less than any alpha that I can possibly pick, right? So what do? If p-value is small, I reject the null, right? So therefore, null is false. I reject that in favor of, in favor of alternative. And what does my alternative say? That the slope, no matter how small it may seem, has to stay in the model.
That's 0, and this is 0, 0, 0, 1. So technically it's larger than 0, right?
Yeah, it technically it's larger than 0, right? But 10 to the power of 97, there is no such thing. It's 0. For all practical intents and purposes, it's 0. Yeah. So technically, yes, there is like 97, 0 point and 97 zeros after that, and then the number starts, right? Decimals. Okay? So for all intents and purposes, what I'm dealing with is astronomically small p-value, right? So I reject the null in favor of alternative. What does my alternative say about my model? Is that a coincidental relationship, or is it a statistically significant model? It is statistically significant, right? So therefore, what I'm concluding from that is mileage is an important variable that actually is statistically related to the car price, okay? That's an important variable. So this relationship is not coincidental, okay? It's got to be very, very slim chance that this is a coincidental, right? Okay, so that's simple linear regression, all right? Now let's take a look at something that's called residual plot. Now, residual plot, did you discuss the residuals in the previous class? Residuals are errors, okay? So here, that plot actually is pretty nice. It illustrates what's going on. So horizontal, I have mileages going on, right? And vertical, I have prices, okay? So overall, the data set behaves like what we predicted, right? For the low mileages, the price is kind of high, and then as the mileage goes up, the price tends to go down, right? And this red line is my regression equation. Now, do you see that most of the points are not on my straight line, right? So here's what happens. Every time when I have a regression, so let me be simplistic about that, okay? So here, that's my mileage, and that's my price, okay? So price starts high, and then it goes down like that. Okay, so I fit the regression, and it goes something like that. All right. And then what happens is I can see that the majority of my points are not on my straight line, not on my prediction equation, right? They're off. So this point, for example, okay? This point corresponds to mileage, whatever it is, x1, okay? This is what I would predict using my straight line equation, this is what the actuality is. Okay, so I'm going to call it my real price and the predicted. So y1 with the hat, okay, with a hat like that. So every time when I make a prediction, almost always I have an error, right? The difference between what it is really and what I predicted, okay? So therefore, error is equal to what I have minus what I predicted. All right? And therefore, what I can do is plot the residuals, these errors are called residuals, right? So error, another word that statisticians are using is residual. Whoopsie. Residual, okay? Errors, residual are synonyms. They mean the same thing. Okay, ideally, here's what I want. I want my line to cut through the center of the cloud so that sometimes I'm under-predicting, right? Sometimes my line is under the point, and sometimes I'm over-predicting. So my errors, positive or negative, they're balanced with each other, right? That would mean that I'm actually predicting on average just right. Okay? I should have as many positives as I have negatives, right? Because otherwise my model would be biased towards either over-predicting or under-predicting. So here is my ideal residuals plot, okay? Half of my residuals should be positive, something like that, okay? And another half of my residuals should be negative, something like that. Okay? And moreover, I should have a residual plot to be looking like a uniform cloud of points with the same thickness all over the place, okay? So residuals variability should be same no matter where I look, okay? That's the ideal residual plot. No curves, no lines, no trends, nothing. All right? So if my residual plot looks like that, this is something that's called homoscedasticity. Something else you may or may not remember from your statistics. Homoscedasticity. Okay? So homoscedasticity is a good thing. That means that your residuals are uniform cloud of points. About half of them are negative, about half are positive, and there is no difference in terms of variability. It's all uniformly looking, okay? Sometimes I don't get that. Sometimes here is what I have, okay? Let me illustrate what kind of issues or problems I may or may not have, okay? So here is the deal, ladies and gents. Suppose I have residuals that look like this. They start off really close to zero, and then as my mileage increases, it looks like residuals are becoming more and more variable. They're kind of all over the place, right? So I can, if I draw the informal boundaries, they look like that. That's not cool, okay? Another pattern of pretty much same behavior would be something like this. If I have vice versa, for low mileage, I have high variability of prices, okay? They're all over the place, but as the mileage goes up, they kind of converge. So again, I have this conic shape going on, okay? So if I have patterns like that, they're called not homoscedasticity, but heteroscedasticity, okay? Heteroscedasticity. So heteroscedasticity, is it good or bad? It's bad, right? If I have patterns like this, behavior like that, that's not looking good, okay? So that means that my model has something fishy going on, right? And I need to fix that. So that is an indication of an issue, all right? So let's take a look at my residuals. Where's my residuals plot? It's right here, okay? It's residuals, price residuals plotted versus predicted, fitted price, right? So what do you think? Is that a well-behaved residual plot or the one that indicates an issue? What do you think? Well, it's easy to tell, right? If it's uniform cloud with the same thickness, that's cool. Is it? No, not exactly, right? Does it look like conic shape to you? They kind of start low, right, and then they increase? Yeah. So therefore, my model certainly, well, first of all, it's not exactly the greatest model in the world with R squared, right, being only 36%, not 100. Second, my residuals plot basically shows me that there might be a problem, okay? So how do I fix that issue? Well, one way to do it is to say, well, look, this model only says that the price of the vehicle depends on the mileage. Is it? Only on the mileage. No, right? Other things are important. What are some other things that may be important in pricing the used car? Mileage is probably the biggest, but what else can there be? In your opinion, what do you think?
The model type.
The model, right? BMW versus, I don't know, Toyota Corolla. Well, not the same, right? What else? Condition, right? Being like poor condition, meaning like run down, right? Versus excellent, almost new, no scratches, no nothing. Yeah, condition. What else?
Manual versus automatic.
Manual versus automatic, right? Automatic tends to be a little bit pricier than the manual, right? Is number of accidents important? If you check the Carfax and it says no accidents, one owner, right? As opposed to 15 owners and 3 accidents on record. Probably it is a factor, right? Sometimes color is a factor, right? Cool looking black car as opposed to like funky looking orange car, right? Number of extra features such as leather seats, sunroof, CD changer, extra loud exhaust, that kind of stuff, right? So there are a lot of variables that affect the car price. And here we're saying that this is a very simplistic model. It says mileage is the only thing that's important, right? Okay, so here's what I'm thinking, y'all. If I will throw more variables into the model, what will happen with the accuracy? How closely my model fits the data points? Will it get better or worse? Better, right? Because I'm adding more dimensions of the reality, right, to my model. I'm taking into consideration more than just the mileage. So hopefully, when I fit a better model, my R squared will go up, right? Let's see, shall we? So let's go ahead and close that one. So we're actually getting rid, we're kind of transitioning from the simple regression into multiple regression, right? Meaning that my predictors are many and not just one, okay? So when you have multiple x's going on, then you have multiple regression. So essentially, here's what I'm looking for. I'm going to say that price, let's add one variable at a time, just for the heck of it, right? We have all time in the world, right? Today. Okay, I'm not going to let you out early. Don't bet on it, okay? So here's what I'm going to do. I'm going to say, I want to find the model that looks like that. Whatever intercept is, numerically, I don't know, right? Plus mileage, my good old friend, because I know that mileage is good, it's a significant variable, right? Plus, I'm going to add another variable, age of the car. How old is the car, right? And what's the common sense? What does common sense dictate you? The older the car becomes, what happens with the price? Gets up or down? Down, right? Same mileage, but older car will be worth less money, right? You would think. Okay, so for now, I'm going to do this model. So, again, I hope that my R squared will go up, right? And we'll see what happens with residuals, right? What the heck? I mean, I have to keep open mind, right? Do it without prejudice. So let's fit another model. Kaboom. Same deal, right? My price is my target. And mileage and the age, I'm going to select them both using control button. I'm going to add them into my predictors. Sometimes predictors are also called regressors. I'm going to regress the price on mileage and the age of the car, okay? So independent variables, predictors, regressors, same concept, different names, right? I'm going to run it, and first of all, let's look at the most important thing of them all. What's the equation, right? Where do I look? Parameter estimate. Here's my intercept. Here is the slope for the mileage. It's actually different a little bit. And here's the slope for the age of the car, right? So let's go ahead and write it down. 2, 1, 3, 4. So my actual equation is like that. Price equals 2, 1, 3, 4. 0, right? 2, 1, 3, 4, 0. Yeah. Minus. Mileage has still minus sign. That makes sense, right? Mileage goes up, price goes down. Okay, so minus 0.01795. 0.01795 times the mileage. That's my beta 1. And minus, I believe, right? What's the slope for my age? Yeah, it's minus 173.9. Does that also correspond to my common sense hunch that I had before? Cars getting older, price going down? Yeah, it's consistent, right? Minus 173.9. minus 173.9 times the age of the car. Okay? So that's my regression equation. Let's again interpret the slopes and the coefficients. Okay? So what happens if I increase mileage by 1? The value of the car will go down, right? Very similar to what we did before. If I keep the age the same, only drive 1 more mile in the car, right? It's very easy to do. Then what will happen to the price of the vehicle? That part will remain the same, right? Age-related part, okay? But because mileage is now mileage plus 1, I have to take my old price and subtract 0.01795 from it, right? So once again, the interpretation of that slope is every time when I put extra mile on my vehicle, all other variables being the same, no changes, right? The price of the car goes down by, what, 1.795 cents, right? That's a fraction of the dollar, right, essentially. So that's my interpretation for the slope. Okay, what's the interpretation for the age? Now I'm going to spin it around, right, and come from a different angle. What if mileage stays the same, but age is getting plus 1? Plus 1 means, I believe, all the ages in the file are in months. How old is the car in months, right? So what happens if age goes up by 1 but mileage stays the same? That means that I didn't drive the car, right? I didn't drive the car in a month, okay? So age goes up but mileage stays the same. So what happens with the car? Well, that one tells me that every time when the car ages by 1 but mileage doesn't change, the value of the car drops but by $173.90, right? That's the interpretation. And finally, that one, we interpreted that already, right? Mileage is 0, age is 0. How do we call that car? Brand new, right? So the value of the brand new car is 21,340, predicted value, right? For the brand new car. Make sense? Okay. Well, let's take a look at how good of the model is that. Remember, we just discussed that if I add more variables, what happens to the accuracy, how closely the model fits the data? Supposed to go up, right? Did it? Remember what it was before with mileage only? It was 35.5%, right? So now my R squared is, oh my God, look at that, 0.77. So these two variables together, they explain about 77% of what's going on in my data, okay? That's a huge improvement, right? So my model is doing so much better. So my interpretation is, because of the 77.3% of the variability in cars' prices are because different cars have variability in mileages and different cars have variability in their ages, right? So these two variables together explain 77% of what's going on. Okay? Now, ladies and gentlemen, let's see if we can make things even better. What do you think I should do? To make even better model, I should throw in, or at least try to throw in more variables, right? So for now, we're going to just try to add continuous variables. I don't know if you noticed or not, but so far we were working with continuous variables, right? My target was price, which is continuous variable, age is continuous variable, and the mileage is continuous variable, right? So I'm using only continuous predictors right now. Let me keep this wonderful tradition, okay? So I'm going to rebuild this model and add horsepower, okay? So let's go ahead and do that. I'm going to click on this one that says fit the model. So price again is my target, right? Now I'm going to select as predictors price, mileage, and horsepower. All numerical variables. So I don't want to get into the stuff that's basically categorical, okay? For now, at least. So I'm going to go ahead and click add, and then let's go ahead and run the model. So what do I expect to see from my R squared? Go up or go down? Go up, right? All right. So, well, first of all, here is my model, right? My model now is, all the coefficients are updated, obviously. Every time when you rerun the model, you have new coefficients, right? It changes every time. So here are my new coefficients, and you can see that horsepower, how does that impact the price value? Positive, right? The more horsepower, every time when I add extra horsepower, keep the age the same and the mileage the same. What happens with the value of the car? It goes up or goes down? It goes horsepower. I'm adding horsepower. It goes up, right, according to that. So if the age is the same and mileage is the same, but horsepower goes up by 1, I don't know, by some miracle of mechanics, okay? Then the car becomes $44.6 more valuable, right? That's the impact of the horsepower, okay? What happened to R squared? Tell me. Did I get a better deal or a worse deal as far as the accuracy is concerned? Better, right? It used to be 77%, right? And now my R squared is 80%. But here's the question, y'all. True or false? This increase doesn't seem like a huge jump anymore, right? Prior to that, when I added the age of the car, it was like, my God, huge improvement, right? Here I went from 77 to 80% in R squared. It doesn't seem like a big deal, right? So could it be that the variable, which one did we add last? Horsepower, right? Horsepower. Could it be that horsepower is not really all that important because it didn't have an impact, huge impact on my R squared? It could be, right? So here is the sad truth, okay, about the regression analysis. Truth is, every time when you add a new variable into your model, your R squared has nowhere to go but up, okay? If you add more variables, supposedly you're building a better model, right? Which models the reality better and better and better. And that comes with R squared getting higher and higher, right? But that's not just a blessing, that's also is a curse, right? Statisticians are inclined to throw all kinds of variables into the model just to make sure that R squared goes up, right? If I have 150 variables, well, hell, I'm going to include all of them, right? R squared is going to be gigantic, possibly, right? Some of these variables may have nothing to do with what I'm trying to model. R squared will go up anyway. For example, if I'm trying to predict the model of Microsoft price stock price, okay, on the stock exchange tomorrow, and day after tomorrow, and in a week, I can use as one of my variables temperature in the city of Newport News. Now, let me ask you, does the temperature in the city of Newport News have anything to do with how high or low Microsoft stock costs on the stock exchange? Nothing at all, right? But, believe it or not, if I add temperature in the model, my R squared will get up, right? It'll get higher. Obviously, I don't want that, right? Because what I'm doing really is I'm adding garbage, right? Variables that don't contribute really. Just for the heck of it, right? Because R squared is getting higher and higher and higher. So, we have to have a way to differentiate between the real improvement, real contribution to the model, and the fake one, right? So variables, we have to be able to discriminate between the variables. Separate the ones that are significant from the ones that, unfortunately, not significant. So, my dear friends, let's discuss the same test, but a little bit modified. So let me go back to the drawing board, okay? Remember how we just half an hour ago discussed something that's called testing for overall model significance, right? For a single variable model, for the simple regression. We're going to do two separate tests, okay? So first, and that applies only to multiple regression, okay? So when you have multiple independent variables, just like we have age, mileage, and horsepower, right? So first test that I'm going to do is exactly the same pretty much test that I did before, but it looks a little bit different. So bear with me for a sec, okay? So testing for overall, and keyword here, overall, model significance, okay? Model significance. Here's what I'm testing. Okay? I'm testing the following hypothesis. My null is going to be that the model is completely trash. It has nothing to do with price whatsoever. None of my variables have nothing to do with the price. Not a single one of them, okay? So that means that if I take the slope for the mileage, it is equal to the slope for the age of the car, and it is equal to the slope for the horsepower of the car, and they all can be set collectively not to 6 but to 0, okay? That means that I can take every single one of my variables in the model and multiply them by zeros, and that will give me just as good of a model, right? Now, if I replace all the slopes with zeros, what does that tell me about variables? Are they important, any of these variables? No, not really, right? Slopes are zeros, whatever the variables are multiplied by zeros, no effect on the mileage, right? So that means that my model is pretty much null and void, right? I don't have a model. So if I find in favor of null, that essentially means that the model is not capital N-O-T significant, right? That's what it means. Alternative would say something like this. It may be that the mileage is important and the rest of them are not. Or it could be that mileage and horsepower is important but age is not, right? So it can be any combination. So how do I generalize that? Here, I'm going to write at least one of my variables has a slope that is not 0. So at least one of my slopes, beta I, is not 0. So out of the 3 that I have variables, right, I have at least one that has to stay in the equation with the slope, whatever it is in my model right now, okay? I cannot just simply take them all out. At least one has to stay, okay? And if at least one has to stay, my model actually is significant. So once again, if I have a hypothesis, I need a what? P-value, right? Where to find it? Okay, so same exact place actually, okay? So I go back to the summary, my output, right here is my analysis of variances, okay? And here is my F ratio, whatever that is, right? And probability greater than F statistic, which is what? Oh, I just saw it. It doesn't matter, right? Because it's less than 0.0001. That means that it's less than 1%. So whatever alpha I choose, it's less than alpha, and I will have to reject the null in favor of alternative, right? So my p-value, let me just say it's 0.0001. It's less than that probably, but it doesn't matter because whatever alpha I pick, 10%, 5%, 1%, p-value is less than this alpha. And again, what do I do if p-value is low? Keep the null or reject the null? Reject, right? P-value is low, I reject the null. So I reject the null in favor of alternative. And what does my alternative say? Is that a significant model overall or not so much? It says that at least one of my variables has something to do with pricing, right? Therefore, considered all together, the model is good and valuable, okay? We can't just discard it. So this is a significant model. So that's step 1. Step 2, now I'm going to have to test each one of my variables, okay? Let's get on with this program. So I'm going to test significance of every single variable in my model, all right? So testing individual variables significance. So I have, and that means independent variables, right? My x's, x1, x2, x3, okay? So I have 3 independent variables, 3 predictors. I'm going to test 3 hypotheses, right? So my first is going to be mileage, and I'm going to do exactly the same thing as I did before for the simple regression, right? So here's my first hypothesis, that the slope for the mileage can be set to 0. By the way, making the variable mileage significant or not? The slope is 0 for the mileage, not significant, right? So null hypothesis is essentially the same thing as mileage is not significant. Mileage is not a significant variable, right? Significant variable. I'm going to abbreviate, okay? So alternative is, no, it is significant. It's got to stay, right? So alternative is that the slope for the mileage cannot be set to 0. So that's my first hypothesis. Second hypothesis, same exact thing, right? Null is going to be that the slope for the age of the car can be set to 0, making age not a significant contributor, right? Variable that can be discarded without much loss of a model accuracy, okay? And alternative, therefore, is the slope for the age got to stay non-zero, whatever it is right now, okay? And finally, the third one is going to be horsepower, right? Null is going to be that the slope for the horsepower, HP, is 0, okay? I don't know how number 8 got there, quite honestly. I pressed something, it's a miracle. Okay, H1, slope for the horsepower cannot be set to 0, okay? So, 3 hypotheses, 3 p-values, right? Where to find them? Well, let's take a look, okay? Where to find them? I have to go to the parameter estimates, and you can see that the last column in the parameter estimates portion, here is the age, right? Slope for the age, slope for the mileage, slope for the horsepower. Last column says probability greater than absolute value of t. That's the p-value that I'm looking for, okay? So all of my p-values, what can I say about them? They're all very small, right? Less than 1/10 of the percent, right? So for all intents and purposes, I can consider them less than a percent. So therefore, here p-value, let's say for the simplicity, 0.001, right? Less than any reasonable alpha that I can pick. Less than 10%, 5%, and 1%. What do I do between null and alternative? Keep the null or reject the null? Reject the null, right? So I'm rejecting the null. And what does my alternative say? Mileage, is it important variable or not? It is, right? It has to stay with slope, whatever it is right now. Same deal with the p-value for the age, right? It's a very small number. I don't know what it is, but it's less than alpha. Any alpha that I can pick. Once again, reject the null. Age is important variable, right? And same thing here. I would reject the null in favor of alternative. Horsepower is important variable, right? So that's the way how I can discriminate between the variables. It will not always be the case. I mean, here we have a lucky sample, lucky example, right? All three variables are important. They all contribute to the model. In actuality, that's how you basically decide which variable has to stay and which variable can go, okay? You test the variables individually and kind of judge based on that. Any questions, ladies and gentlemen, about that? You're awfully quiet. Say meow. Meow. There you go. Okay. We have about 20 minutes remaining. In the time remaining, I want to discuss a couple of things. Okay. Thing number one. For the multiple regression, we need to check one more thingy. Okay. And that thingy is called bad condition multicollinearity. Let me ask you this question. In all these models that I built, I kind of assume that my dependent variable is the price, and price depends on a whole bunch of other things, right? Mileage, age, horsepower, etc. Okay? How do I call these other predictors? Mileage, age, horsepower. What's another term for these variables? Not dependent like y, but independent, right? Variables have to be independent from what? From each other, primarily. Okay? So, in all of these beautiful deliberations that I put out today, I'm kind of silently assuming that age is not related to the mileage and is not related to the horsepower. But in actuality, let's kind of think about that. Wouldn't you agree or disagree with this statement? As the car gets older, the mileage goes up. True? Yeah, you drive the car, right? It's not just sitting there, right? So age goes up, mileage goes up. So it's not absolutely crazy idea to believe that these two variables, mileage and age, are correlated with each other. Did you discuss how do we measure the degree of correlation, the coefficient of correlation? No? Okay, let's discuss that, okay? Two variables, x and y, can be correlated highly, moderately, or weakly correlated with each other. So, the degree of how two variables coexist together is measured by something that's called coefficient of correlation. Okay? Typically for the coefficient of correlation, we use letter R. Coefficient of correlation can be between -1 and +1. Okay? The closer the coefficient of correlation to 1 or -1, the better it is. That means that these two things are highly correlated with each other. The closer the coefficient of correlation to 0, the worse it is. Okay? If the coefficient of correlation is pure and accurate 0, that means that x and y have nothing to do with each other. Knowing x will not provide you any information about y. Okay? It's as if you have no model going on at all whatsoever. So, therefore, here is the informal scale, sort of, okay? Informal scale of how to judge the strength of correlation. Let's kind of put it out. Now, what I'm about to write actually is not an exact science, it's more like an estimate, okay? A set of rules or generally adopted conventions, if you will, okay? So if the absolute value of the coefficient of correlation is between 0.7 and 1, so in other words, it's either close to +1 or close to -1, okay? Then we're going to say that this is a strong correlation. Correlation is strong. Okay? If, on the other hand, the absolute value of the coefficient of correlation is between 0.3 and 0.7, I'm going to call it, if you would have to guess, what would it be? Moderate, right? So it's a moderate correlation. Correlation, okay? And finally, if the absolute value is between 0 and 0.3, how do I call that? Weak correlation, right? So, coming back to the question of independence, right? Remember we discussed that. Variables have to be independent from each other, right? So, two variables are considered to be not independent but highly correlated if the coefficient of correlation between them either between 0.7 and +1 or -0.7 and -1, right? Either way, it's a strong positive or strong negative, it's equally sort of equally bad or equally nice, depending on how you look at it, okay? So what I'm going to do right now is calculate the coefficient of correlation, mutual correlation between all of my independent variables, okay? And if any of my independent variables highly correlated with each other, then I'm dealing with bad problem, which is called multicollinearity, right? So multicollinearity, I'm going to write it out. Multicollinearity is a bad condition when that happens, right? If any of my independent variable x not actually independent from each other, on contrary, they're strongly correlated. That makes them dependent, right? That violates the whole assumption behind this thing, right? Make sense? They have to be disjointed, disconnected. One changes, doesn't affect the other one. That's when I call them independent. But if one goes up, another goes up at the same time, they kind of go together, that's not a good situation. If I put them both simultaneously into the model, that would pretty much indicate to me that, hey, you know, it's as if I'm putting the same variable twice, right? And that can create all kinds of weird problems with regression, okay? So let's go ahead and take a look if we have this problem with our model. Oh, by the way, here's my residual plot. What do you think? Is it a relatively well-behaved plot? Yeah, I'd say so, right? It pretty much has heteroscedasticity, right? No weird shapes, no trends, no curves. Well, I mean, you can think that, hey, this is the curve, right? But that probably can be fixed. But that requires completely different approach, which we don't have time to discuss today. So let's get with multicollinearity, right? Let's get on board with this program. How do I check for multicollinearity? Simply, I need to create how many correlation coefficients? Well, I have how many independent variables in my model? 3, right? Age, mileage, and horsepower. So I need to correlate age and mileage, age and horsepower, right? And then after that, mileage and horsepower, right? And that would be everything. So let's go ahead and do that. I go into the Analyze menu, Multivariate Methods, something that probably you never did before, right? Would jump. The very first option, multivariate, okay? And I'm going to select my variables, which I believe, at least for now, they're independent, right? Okay, so that would be age, right? And I hit Control, mileage, and horsepower. These 3, right? These are my x's. I exclude price, I exclude y, right? I want them to be highly correlated with y, right? That's the basis of my regression. They're highly correlated with y, and that's what allows me to build a model, right? Now that's okay, but I want them to be mutually non-correlated, right, among themselves. So I add them into the y columns, and then I click OK. It gives me a couple of things. Thing number 1, it gives me correlation matrix. Each one with each other one, right? And it gives me also this graphical representation. Well, first of all, let me point out, what do you see on the diagonal of this matrix? Tell me. All ones, right? Age with age is perfectly correlated, right? That's not too surprising. If you can imagine the graph, horizontally I have age of the car, and vertically I have the same thing, right? So if I have the car that has, for example, 20 months old, right, the age of the car, I have 20 horizontally and 20 vertically, it goes on the diagonal line, right? So all points are perfectly aligned horizontally, right? Oh, I'm diagonally, right? So a variable is always perfectly correlated with itself. That's not a big mystery. So that's not what I'm looking at, right? So I'm going to completely ignore things that are on the diagonal. What I'm interested in are numbers off the diagonal. And once again, tell me what I'm looking for. What kind of stuff I'm looking for. These are mutual coefficients of correlation, right? What will trip me off? Make the alarm bell to go off. If any of these coefficients of correlation are either above what? 0.7 or below minus 0.7, right? That would be an indication to me that, hey, something fishy is going on, okay? Now, remember our discussion about how age and mileage probably are closely related with each other, right? You drive the car more, it gets old. Well, other way around, right? The car gets older, it gets more mileage, right? Well, what do you say? Age and mileage, what's the correlation between them? You see that one? 0.55, right? According to our informal classification, is it strong, medium, or low? Medium, right? Medium is not, and that basically is in line with my kind of hunch, right, that I had before, right? They're correlated, but are they strongly correlated? No, not necessarily, right? Because sometimes I'm guessing, people don't drive their car for a long time, right? So, or maybe they use it for a very short commute, right? So the car ages faster than it gets mileage, right? On the other hand, if you talk about rental cars, like if you look at 1-year-old car, it has like 50,000 miles on it easily, right? Crazy, right? Car didn't age that much, but it has huge mileage. So, therefore, there is not a perfect correlation. But in general, yes. But is that a problem? No, it's not, right? Because correlation is not strong, right? So that's okay. How about age with horsepower? Is that a problem? You tell me. Correlation coefficient minus 0.1763. Is that a problematic number or is it an okay number? What am I looking for? 0.7 or minus 0.7, right? Anything beyond these boundaries is a problem, right? Is that beyond the boundaries? No. It's close to 0 actually, right? So that correlation is weak. That's okay. That's what I like to see, right? How about mileage and the horsepower? How would you characterize this correlation? Mileage and the horsepower. Strong, medium, or weak? Say something. I feel awkward. Yes?
So what are we actually comparing? Are we comparing like, so I know we're not looking at the diagonal in the middle, but so we were comparing like for age, the 0.5509 and the negative 0.01763?
We're looking for all of these things. So my model has no issues and no problems if all of these correlations are not strong. They have to be either medium or weak, preferably weak. That would mean to me that none of my independent variables are strongly correlated with each other. That's what I want to see, okay? And how do we define strong? If the positive is more than 0.7, if it's negative, it's lower than minus 0.7, right? Kind of extreme values, close to plus 1 or minus 1, right? And my cutoff point is plus 0.7 or minus 0.7. So if anything between these two lines, that's either medium or weak. I can live with that, right? But if it's outside, that's where the problems start to show up, right? That's essentially what we're looking for. So minus 0.3452. Is it strong, medium, or weak?
I have a question.
Sure.
So if it were to have a strong correlation, would you remove it from the linear?
Excellent question. What happens if we find, let's say, for example, just hypothetical, right? Age and mileage are highly correlated. Not 0.55 that I have, but 0.79, right? Oopsie daisy. The answer is yes, probably I would need to remove one of them, and that's where from science it becomes an art. Which one? Don't know. Let's try both. Like take one out and see what happens, take another out, see what happens. But if I have two variables that are highly correlated, essentially I'm accounting for the same variable twice. That's what happens, right? I'm putting the mileage and then kind of mileage again, right? Yeah, so you're absolutely right. If two things are strongly correlated, they probably shouldn't be in the same equation together. That's exactly right. Okay? So, do I have a multicollinearity problem in this case? No, I don't, right? None of my coefficients of correlation are high, right? 0.7 or above, or minus 0.7 or below, right? So therefore, thank God, I don't have an issue with multicollinearity. And that's what I want, okay? If you have a multicollinearity, that's an indication that, hey, you have problems. You probably need to work on your model a little bit more, okay? Be a little bit more careful how you, which variables you select, okay? Does it make sense? Okay. One more thing that I wanted to point out is, I don't know if, oh, hold on, let's go back. I don't know if you noticed or not, let me quickly recreate, I believe I closed the analysis. Recall, run. I don't know if you noticed or not, but when we discussed the goodness of fit, or summary of fit, there are actually two R squared. Okay? One R squared is just plain and simple our good old friend R squared. Another is adjusted R squared. So the natural question is, when we discuss how nicely, goodly, your model fits your data, which one do I use, right? Closer to one the better, but which one do I use? And when you're dealing with simple regression that contains only one variable, okay? It doesn't really matter, they're very close to each other, practically the same, okay? The big difference starts to come in, you will start to see big difference if you're dealing with multiple regression, just like what we have here, right? More than one independent variable. Here is the difference, ladies and gentlemen, okay? Adjusted R squared, let me give you the short answer and then long story after that, okay? When evaluating how nicely your model fits the data, you use adjusted R squared. That's the preferred way, okay? Now, the question is, what the heck's the difference, right? Adjusted for what? Remember our discussion earlier today that the more variables I place into the model, the better it becomes, right? My R squared goes up and up and up and up. That creates kind of a desire on the part of statisticians or business analysts to put every single thing that they can find into the model with the sole purpose of getting R squared high in the sky, right? I did a great job, my R squared is 0.8. It has 250 variables. Oh, great. You're a great statistician. Now we have to use it and interpret it, right? R squared adjusted was designed to punish for extra variables, okay? So here is the formula. I believe the formula actually is in the textbook. I don't want to pay too close attention to the formula, but here. Adjusted R squared is 1 minus n minus 1 n minus p minus 1 times 1 minus R squared unadjusted. That's as far as I remember, okay? What's the bottom line? Here's the bottom line, okay? Let's say, and n here is the sample size, and p here is the number of predictors. In other words, number of independent variables that you throw into the model, okay? Suppose, for example, I choose 500 predictor variables, okay? That makes my numerator small, right? Smaller compared to the, denominator smaller compared to the numerator, so that number is probably going to be greater than 1, right? So if I throw in a lot of predictors, my number p is high, my R squared is going to be also high, right? So therefore, that one difference is kind of going to be smaller and smaller and smaller. But now I'm kind of blowing it up with this factor, okay? And I'm subtracting higher number. So long story short, what will happen, I understand that it doesn't make much of a sense, right, when you're looking at it. What's going to happen is R squared adjusted will tell you that, hey, one variable is okay, two variables are okay. So your adjusted R squared will go up, right? You add few variables, that's okay. But once you start overbuilding your model, throwing in too many variables, it will start punishing you, okay? So essentially, adjusted R squared is the way to keep the balance between variables that are relevant, variables that are not relevant, plus having too many variables in the model to begin with, okay? So once you start kind of exceeding certain threshold, once your model is getting too complicated, too many predictors, okay, your adjusted R squared will start going down. The adjusted R squared will start punishing you for making the model too too complicated, and probably build on variables that have nothing to do with what you're modeling. Okay? So it's kind of a way to keep things in check, right? So statisticians who like to throw in more and more and more variables, adjusted R-squared will start catching up with them at some point in time and say, hey, now from that point on, you add more variables, I will punish you. R-squared will go down. So we will not get this wonderful performance anymore, okay? Now you have to pick and choose the variables that you really want to keep. Kind of stick with things that are important, that represent the structure of your model, and don't put in the noise. Variables that don't contribute, but kind of mud the picture, okay? They kind of obscure the view, okay? Things that are not that related, keep them out of the model, keep it clean. So that's what adjusted R-squared does, okay? And that's the preferred way to measure how well your model fits your data. Does it make sense? Kind of, sort of? So the more irrelevant variables you put into the model, the lower your adjusted R-squared will get. It will start telling you that, hey, you're doing something wrong, okay? Cut down on the variables and keep the ones that really are important, and everything else, you just leave it alone, okay? Any questions? Is it system overload? Too much information for today? I was going to show you one more data set. Are you up to it? Or not really? No? Okay. Well, we're out of time, right? Okay, so that's it for today. I hope it was informative.